Okay. We have only one loop in this circuit, and we're writing down the
I don't know if you know.
What do you think it says? This
voltage drops. Okay. We have no nodes, one loop, so there's only one equation to write. Now my voltage drop across the voltmeter, if I'm going counterclockwise, is V, right? Now, let's assume that I is in this direction. There's only one current, okay? So the voltage drop has to equal I times R, right? Plus the voltage drop across the capacitor, plus the voltage drop across the inductor. And of course, we want to write expressions for these things, right? So what's the voltage drop across your capacitor? Q over C, right? Because capacitance, C, is number of volts per unit of charge, right? Or, I'm sorry, charge per number of volts, okay? So you can rearrange that and find that the voltage is charge over capacitance. Now, what's inductance? Well, a loop, changing current through a loop changes the magnetic field through that loop, which then opposes the change in current, okay? And that's the whole idea of an inductor. And the inductance is just then what you multiply by the rate of change of the current to get that voltage, okay? So, let's see now. I is in this direction. If di dt is positive, then what's the voltage drop across your inductor? Well, it's going to create a voltage back this way, so voltage will drop between here and here. Okay? So that's going to be then L di dt. Okay? Of course, we want to express all this.
So it's not a negative L because of the direction it's going, right?
It's not a negative L because here's our positive
Right.
direction.
Due to the direction, though, standardly it's negative.
Yeah, actually, yeah, okay. Anyhow, here's what we got, right?
Okay.
Okay?
We're going.
So, the point is,
Yeah, I think the current should be negative, shouldn't it? If we're going this direction and the current's
yeah, all
going
these
opposite.
should be negative. Okay?
Oh, okay.
Uh,
I didn't
no,
know.
these are drops. I'm sorry, these are voltage drops. Your voltage drops across the resistor. It drops across the capacitor. Now, there's a little tricky thing we got to do. We got to assume that this is a positive end of the capacitor. Voltage is dropping from here to here. So if your Q is negative, then it's this one that's positive, right? Okay. Because one of these is positive and one's negative, and there's kind of a little ambiguity there you've got to think through. Okay. And then you got to drop across here due to the inductance. Okay? Now, let's call this V sub S for voltage of the source. Just so we don't get, yeah, we got subscripts and all the other voltages, even though we've already replaced these. We'll still keep voltage of the source here. And voltage of the source doesn't have to be constant, but I've drawn it as a constant voltage here. Okay? So, we want to do this in terms of just one variable. We've got two variables here. We've got Q and we've got I. So how are we going to do that? Well, y'all were already into that question. Now the current is dq dt. Okay? And then we have Q over C And then if the current is dq dt, then di dt is the second derivative. Now this is nothing new, we've already seen it. Okay? So we could write the equation as L Q double prime plus R Q prime plus Q over C equals voltage of the source. And this is a simple second order differential equation, easily solved if your VS is something you can easily solve for. Okay, either by undetermined coefficients or variation of parameters, right? So if you have a sine function here, it's easy. You just let Q be some arbitrary linear combination of sines and cosines, and you figure it out. And the homogeneous equation is really easy to solve. Okay? So nothing to it, right? So we'll defer the solution to this and the interpretation in terms of what's going on here. Because right now we're just looking at how you write down the equations for the loops and what you get out of them, right? But we can easily solve this equation, and we will, and then we'll interpret it, okay? Okay, well, let's look now at another circuit. And I'll draw that for you, and then we'll take a look at it.